Hello! Thank you for bearing with me, speaking remotely while I could not figure out my childcare responsibilities in time to travel. I want to start by thanking David for letting me be part of this exciting project. I joined the project relatively late in summer 2021 when they already had their QAs done and doing experiments, so I was starting with a fully operational scanner already. The reason why I joined was basically this figure from his grant, where he said that he aims to have 6 voxels across cortical depth, which would be really, really cool for layer fMRI, a field that I care about. However, it's also kind of a physical challenge that I thought I could contribute a bit. So you know the scanner? It's a 70 scanner with an impulse gradient, and at the beginning we used this 96 channel coil from Jajan. And at that time, I was in the Netherlands in lockdown with my infant son and my daughter just about to be born. So I was really benefiting from this remote scanning system that Alex and Sam had set up for me to operate the scanner via Zoom. And this was very helpful to kind of do the interactive kind of optimization of the sequences. And even then it took like 10 sessions to get everything in order for us to have very exciting experiments. I used 3D EPI from Rüdiger Stirnberg, and because it gives us a lot of flexibility to deal with the kind of artifact level, but also the very different noise regime that we expect at these very small voxels, to have 6 voxels across cortical depth, 0.45 millimeters or so. Even with the very exciting coils of 96 channels, still there, we had to be conservative and not use a lot of crapper, even no crapper in plane at all, because we did not want to deal with G-factor noise amplification. Instead, we did a lot of segmentation here for an inversion recovery sequence where we have an inversion, then multiple segments acquired for bold and vaso, and then the remaining segments are then acquired in the next inversion recovery period. And then we spread those out in the KY direction for most efficient unaliasing in that direction for grappa, to have 2 simultaneously acquired K-spaces of vein-free fMRI vaso and bold too. And we had a lot of fun, these fun nights. Every Monday, after I brought my son to bed, I came back to work to connect to Alex's Expert Eye View, scanner control, and hunting artifacts. And we were hunting different artifacts than Indiana Jones, but still it kind of felt like this exciting time. It felt adventurous. And also due to the fact that at that time in Netherlands there was curfew. So I took my bike without the light, went on the back street so nobody saw me, to then have a lot of fun artifact hunting. We had our arch nemesis, the Pali, and I'm not referring to the Hindu gods of the Pali scripts, but rather the power absorption limiter, this kind of Syngo-Siemens error that was coming from weird interaction of using memory on the Mars with these very many channels, but also the ice pad reconstruction using memory that should be allocated to SAR. I don't know. They at the end ended up, I think, changing the infrastructure and architecture there completely. And it took maybe 4 weeks of unsuccessful scans because the scanner would just stop randomly. We had a lot of fun figuring out blurring issues with the nonlinearity corrections of the gradients, inflow effects in vaso that we had to deal with, but also very unconventional spikes or eddy current artifacts. Different than what I'm used to at conventional 0.8 millimeter layer fMRI resolution. Suddenly these crushers and rephaser blips became a problem because they conventionally use the maximum slew rate, and it's just overkill to use 900 slew rate from the Feinbergatron just to make the blips a few nanoseconds shorter, right? So we had to relax them a bit, understand where they're coming from, and then also still optimize a lot with the echo spacing to deal with the different levels of artifacts that you're getting on certain parts of the spectrum. And then at the end, Alex went in, looked at a flickering checkerboard for 45 minutes, and we got those kind of images, which just got me super excited because I could, for the first time at these resolutions, see that even for these thin cortical areas of the visual cortex, you see these stripes of these layer groups. And I know it's wasteful to do these kind of transversal slices, even though you only care about the visual cortex with all these uninterested areas in there, but still we wanted it to have kind of directly see in EPI that you're looking at a brain, and also to have a feel about the sharpness of the images and to see that we indeed have 6 voxels across cortical depth as David promised in his grant. Another nice feature of these resolutions was that kind of you see these subtle differences of layer fMRI that usually you don't need to consider. For example, in the underlay of these images, for the canonical layer model, layer 4 is somewhere at the center and it's relatively thin. However, at this resolution, it matters to look at these fine nuances, namely in visual cortex, it's actually slightly different, that we have very thick layer 4s and layer 4C beta is actually quite deep in the bottom 25% of the visual cortex. And also in humans, different to carnivores or rodents, we have these very thick layer 2, 3, which might be responsible for this superficial peak over there. So I was really excited. I thought, okay, my work is done. David got what he promised in his grant. I sent us the image and told them that they can cancel the remaining scan slots until the ISMRAM deadline. Well, it went differently because 30 minutes later, David called me on my cell phone saying that, yeah, these 0.45 millimeters are nice, but if we can do 0.45, maybe we can do better. So we went back, continuing our routine of Monday scans, and until the deadline ended up with 0.39 millimeter isotropic. And even there, I don't think this is really the physical limit, because even there, when you look at the raw time series movies here, you do see that there is noise, but it's not really the salt pepper noise that you would expect for a thermal noise dominated regime. So I think with more artifact hunting sessions, you can go to higher and higher and higher resolutions still until you ultimately hit the thermal noise limit. And at the end, I was glad that David pushed for more scans because it just gave us more data also across sessions that we could combine to look at also more areas. For example, here that's just barely visible, to see enough structure, for example, with respect to the angio architecture that you see in these multi-echo GRE data as these diving veins, additional to these very deep layer 4 here. And at those diving veins, we, as expected, saw a lot of bold signal changes from these oxygenation changes, but at this resolution, it's not so simple that just the vein is always a problem. Namely, some of those veins actually did not show a huge bold bias. So the within voxel and the cross voxel dephasing is different, obviously, across resolutions. For blood volume, we saw these many interesting features, that having these double peak that sometimes kind of merges into a single peak, interestingly, but also these kind of double points along the cortical ribbon, which I could not see before at conventional 0.8 millimeter layer fMRI resolutions. And those could be very insightful to interpret signals with respect to vessels or columnar structures. And to put these resolutions into perspective, we also subsequently downsampled the data further and further and further with two important features. That first of all, you see that these nice double humps here kind of go away for conventional resolutions of 0.7, 0.8. It might still be possible with different partial voluming to look at different neural activity in upper and deeper layer groups, but basically you lose the Nyquist sampling of these two layer humps. But importantly also, we lose a lot of contrast. And namely here we have a nice decent effect size of these different peaks with respect to a baseline in between, and this completely goes away as you go to lower resolutions. You might have more SNR, but the contrast to noise ratio is actually not directly proportional to the SNR there, because we lose a lot of contrast. And to put all this into historical perspective, I think these resolutions are just a direct manifestation of Moore's law of fMRI resolutions, where every decade we get about an order of magnitude better in the voxel size. From 0.1 milliliter in the early 90s to now 0.1 microliters. And for each stage, for each magnitude along the decades, new insights about the brain can be made. Namely, for those kind of exciting experiments in those days, you still had to kind of assume that every neuron in the entire brain area is doing the same thing. Or even with 1 millimeter, you can only have a single layer model. So you still need to assume that each neuron across the cortical depth is kind of doing the same thing. And for conventional layer fMRI at 0.75, for example, you can just barely distinguish two layer groups like feed forward and feed back. But we do know that the cortex is more complex, right? There are more than two layer groups and there are a lot of interactions. So I'm really excited to see which kind of new neuroscience questions can be answered with these resolutions at the Feinbergatron scanner. And if you want to browse some of those data on your own, you can do so, for example, directly on OpenNeuro in the browser to look at activity maps or TSNR maps in your web browser if you want. So after having chased the resolutions here, David invited me over sushi at ISMRAM in London and said that he liked my whole brain movie watching results and that I could use his Feinbergatron scanner for it. So for this project, then the scanner was really fine-tuned already. A lot of these issues were already solved. It was much easier to use. And at that time, again, Alex Beckett helped a lot, as well as Samantha Ma. And you can see the kind of coverage that we were aiming for. The residual artifacts that we were trying to solve were referring to kind of segmentation noise and eddy currents that we could kind of mitigate with a dual polarity readout averaging approach to help our TSNR. The remaining errors were more kind of further down the line in the processing, namely that the matrix sizes that we had were so huge that basically exceeded the nifty file types, right? We had more than 2 to the power of 32 voxels as implemented in most of the software packages, so had to improvise there. But also we optimized it a bit with respect to getting eye tracking done inside the small bore, and to basically directly also have the directions of the optical nerves inside our fMRI, so to kind of track the kind of the gaze position directly from the MRI data. So we ended up with a protocol of like this, of 0.64 millimeters, again, threefold segmentation across the 3 directions, giving us these kind of raw data, which make me really excited. Like to put this into perspective, on our Terra with the mostly closed protocol, this is what we get. Even with less CRAPA and lower resolution, we're still much more limited by thermal noise. And those raw data then also could be transferred to nice connectivity maps, where in some brain areas there we do see these additional subdivisions of different layer groups that I could not see at lower spatial resolutions. But overall, I was a bit disappointed. Like based on the EPI itself, it looks like we have a very high localization specificity and crispness. It's not looking very blurry. There are a bit of distortions left, but it looks better than any structural scan you would expect from a normal scan. But still, a lot of functional responses in these connectivity maps kind of look blurry. So it seems that these recurrent connections basically always engage everything. The most exciting things that I found were these kind of deeper brain structures, something like those networks, where for conventional gradients, the readout just takes so long that phase errors accumulate and the signal decays too fast that you never get that. With the Feinbergatron, we could even see like substructures at these 0.6 millimeter resolutions, which I found very exciting. So to conclude, 0.39 millimeter resolution is doable at a Feinbergatron scanner. This means that a conventional 3 millimeter voxel with 700,000 neurons now is subsampled with 500 subvoxels that only have neural populations of 1,500 neurons left within them. And if you care less about a Nyquist sampling of the individual layer groups, even in these thin areas of V1, you can also use the power for whole brain imaging, for example, at 0.6 millimeter resolution. So with that, I want to thank David again and his team. It was a pleasure to work on this layer fMRI best scanner in the world. And I also want to thank the companies here, because there was a significant industry touch in this project, which was kind of new to me. And I believe that a reason why scanning got so much smoother was also because they rearranged things, they fixed things. And I think it's a really impressive achievement from David to manage this. Like he managed to get Siemens to build this head gradient, where earlier other groups also tried to get him interested in that, but he managed, maybe because he has a company on his own, or he managed to get Jajan work on these exciting coils in Berkeley right during an international travel ban to the US. He just made it happen, right? So congratulations on the scanner and managing that. In my last slide, I also want to advertise the 6-layer fMRI dinner on February 8th. And the speakers are very familiar to you, also from this workshop. And this time, the layer fMRI dinner will be themed about layer fMRI and its interaction to industry. You can join via Zoom. Thank you for your attention.